Anyway, I think enough time has passed to allow all the latecomers to arrive. So it's probably time to open today's session. So hi to everyone who's joined. Now asked me to be the host today, so it's not always him. And I think for me it's a particular pleasure because I get to introduce two people whose work I'm really enthusiastic about. And some of this work was carried out in my lab, which I'm really enthusiastic about having other people find out about. So in today's consciousness talks, we have two great speakers, we have Corinne Bareham and Bruno van Swinderen. Each of them will talk for about 10 to 15 minutes, and that will be followed by questions and answers for a maximum of a total of half an hour for each speaker. And once the hour is up, then everyone is of course welcome to stick around, and we can open the discussion up more to any kinds of connections between the talks, or if anyone wants to address either speaker at that point, that would be great. So yeah, we will start with Corinne Bareham. Corinne did her PhD at the University of Cambridge. This was followed by postdocs at University of Queensland in Jason Mattingly's group, and then again back in Cambridge working with Srivas Chenu and Tristan Beckenstein. And then she got a New Zealand Neurological Foundation repatriation fellowship to come back to her home in New Zealand, and she carried out that fellowship in my lab at Victoria University of Wellington, and she recently got an independent position at Massey University. Yay, congratulations, Corinne. And a Marsden Fast Start grant, which to those of you who are not from New Zealand is a pretty big deal, to continue the work that she will be telling you about today. So Corinne will be telling us about investigating the neural mechanisms of spatial attention biases during sleep onset. Take it away, Corinne.
Thanks, David. Can everyone see these slides okay?
Yep, I think so.
Okay, great. I just switched the screen share. I wanted to make sure it was working all right. Okay, great. So thank you. So I'm just going to talk today a little bit about the Neurological Foundation project that we're working on at the moment. And I just wanted to start with just going through the experimental model that we're using. So we can think of consciousness in these, and different states of consciousness in these two constructs of awareness and our level of wakefulness. And I'm particularly interested in understanding the transition between these states, so from conscious wakefulness into the early stages of drowsiness. So this transition can be used as an experimental model to characterize how cognitive processes begin to fragment. And in particular, I'm interested in how, as our wakefulness begins to diminish, how that impacts our awareness, or in particular, our spatial attention. So very briefly, the task that we're using. So we present a jittered random weight to avoid any expectation. We present a tone, so that can be on the left or the right side of space, and then we have a response window. And those tones are weighted towards the subjective midpoint, so they're quite difficult, so it sort of leads to a bit more uncertainty. And it's a forced choice, so they have to respond with either left or right, and the responses are spatially mapped across the body. And what we found back in 2014 is that the way that spatial attention diminishes is actually asymmetric. So here I'm showing you the error rates on the task, or the error rates for localizing tones. And you can see that as people become drowsy, the difference from their awake performance, there doesn't seem to be much difference for right-sided tones, but there is a substantial difference in their ability to localize tones on the left side of space. So they're incorrectly saying that these tones are on the right. So they seem to show this rightward bias in spatial attention as they drop off to sleep. So one model that essentially could sort of explain these results has come from Corbetta and Shulman's model of the ventral attention network that interacts with the dorsal attention network. So it also leans on the spatial neglect literature as well. So this idea is that the ventral attention network, which is involved in maintaining general wakefulness and arousal, this is a right hemisphere specialized network based on the projections of arousal projections from the brainstem. And this interacts with a more bilateral dorsal attention network, which is involved in shifting and orienting spatial attention across space. And they suggested that damage to that ventral attention network leads to these spatial attention biases that you can see where attention is biased towards the right side of space. But with the neuroimaging literature, there are some other models that have also had some level of support, even the quite recent neuroimaging literature. So one being the right hemisphere dominance model. So here you can see I've represented the allocation of spatial attention resources from the right hemisphere onto both sides of space with these blue lines, and the left hemisphere is allocating resources to the right side of space. And there's quite a lot of support for this, but also still this idea of having a more bilateral sort of interhemispheric model where each side of the hemispheres, each side of the brain is allocating attention to either side of space. So there's quite a lack of consensus in understanding how the brain is actually supporting healthy spatial attention and what's happening in the case of spatial neglect. So our approach is we bring people into the lab, healthy people, and we ask them to do this tone task, this localization task, while they're kind of invited to relax and drop, into the early stages of sleep. So we recline them and we give them a blanket, and we record EEG at the same time so that we can tell when they're becoming drowsy using this direct physiological measure. And before they come in, we actually get a structural MRI scan as well. And we do this so that we can look at the neuromarkers of interest from the EEG and map that to their structural MRI using source reconstruction. So by doing this, we can use the functional data to localize a site that we would like to go and TMS versus a control. So this allows us to take a stronger causal approach to understanding the neuromechanisms that are underlying these spatial biases that we're seeing as we become drowsy. So the idea is that people will come back into the lab after they've had their data analysed and their site chosen based on the functional data. They'll do 20 minutes of the same task, followed by theta burst TMS to the experimental site or a control site, and then they do the same task again for 20 minutes. But today I'm just going to show you some of the results from this first session, so the EEG first session, and some of the source reconstruction results. And at the moment we're currently just going through the piloting of the TMS. So just to start with the behavioural data, so this is what we've come out with from 43 participants that we've run through session 1, and you can see that we've managed to replicate the effects that we saw in 2014, where the error rates for the right side of space don't seem to change from awake to drowsy periods, but actually it's these left error rates that do increase substantially as we become drowsy. And we can look at this as well with signal detection theory, and we see that D prime seems to decrease when we become drowsy as well. So that's a nice sanity check that we are still seeing people doing what we anticipate they'll be doing when they drop off to sleep. And I'm just going to show some very preliminary data looking at the inverse solution of the neurocorrelates that seem to be underlying this effect. And I've just got a little video that I've put together of a single subject. So if you think about the logic of when it comes to choosing what site we want to TMS, we're going to be delivering inhibitory TMS. So we want to disrupt people's ability to correctly localize tones on the left. With the idea that the inhibitory TMS, if it does have an effect, it would lead to more left errors, so incorrectly saying that the tone was on the right. So to make that decision, we're looking at the correct trials to see what parts of and this is from the event-related potential data, we want to see what regions seem to be active when we're awake and correctly localizing on the left, and we're subtracting from that the drowsy performance. So the two source maps are being contrasted against together. So the timer is a little small, so I'll just take you through it when I play this little video. And just to talk about the scale here as well, the scale is an intensity scale. So we're looking at the regions of the brain that seem to have difference between awake and drowsy for the left correct, and obviously yellow is the most intense in that difference. So early on, so we're looking before 100 milliseconds, there's not a lot going on, but around 140, 60, we see little activations in the temporal cortex and then into the parietal cortex. And as we reach sort of 300 milliseconds after the tone, we start to see these more widespread and diffuse networks across the front and the parietal areas of the brain. Now what we're looking for is obviously a region in the right hemisphere. So this area looks quite promising given the intensity map that we have. And I've just turned the brain around here to show that you can see that this area, this supramarginal gyrus area, is still active in the left hemisphere, but very much less so than on the right hemisphere. And what we can do as well is, this is just a static image, but we can also change these maps to show the direction of the difference. So what these maps mean is that the more positive or more yellow differences are regions of the brain that are more active when you're awake versus drowsy, and the blue areas are those regions of the brain that are more active when you're drowsy versus awake. So this right hemisphere area, which looks like the supramarginal gyrus, looks like a really promising area for this particular individual. And when we contrast that as well with what's happening on the right correct trials, we see it is still an area of interest, but again the intensity is much lower. So the criteria, the scientific criteria that we're taking to choose people's individual sites is looking at a region of the brain that seems to be more intensely activated on the awake versus drowsy contrast for left correct, and we're making sure that that area is more strongly activated on the left trials than the right trials, and we're looking around 120 to 300 milliseconds after the tone as well. And so looking at a region of the brain that's more consistently active during that time. So what I've done, just to give you an idea of what the individual sites are going to look like, so sort of localizing this area of the brain that could be underpinning these rightward shifts in biases with low alertness, is I've projected the individual sites from the 43 participants onto a standard template brain. So this is kind of what it's looking like at the moment. So you can see there's quite some variability between the individual sites that are chosen. Some are sort of edging towards inferior frontal, and some are towards the angular gyrus, but primarily there seems to be two real hubs of where these kind of neurocorrelates seem to be coming up, and that's in the supramarginal gyrus and also in the temporal parietal junction, so the STG. So this is interesting, I guess, from the perspective of if we look at the regions of the brain that are often underpinning the spatial neglect, and also the regions in the ventral attention network, we can see that the SMG and the SCG do seem to be the two sites that map onto that quite well. And I have to say, although some of the individuals did show regions in the front of the brain, I've chosen these sites in the parietal lobe because for the purposes of TMS and the logistics of that, these are the sites that we can access more easily without causing too much discomfort for the individuals. So this is very much still a work in progress. So this is what we're working on at the moment, looking at some paired sample t-tests to look at the significant difference between these contrasts. And I'm also looking at producing a similar map as this one for the drowsy left areas as well, to see what's going on there. So very quickly, thank you to everyone involved in the project. Tristan over in Cambridge is an AI, and obviously David as well. And I want to thank Elliot, who has collected much of the session 1 data with the EEG and the drowsiness. And thanks to Maya as well, who's currently piloting the TMS. And that's all I've got. So happy to take questions.
Thank you, Corinne. And I always forget where the clapping icon is, but it's awkward on Zoom. We still haven't found a good solution for that. Okay, so I guess if anyone has questions, Nal has already put during the talk a few questions in the chat here. And I guess we'll start with that. But now you're also monitoring the YouTube channel as well, right? So we might alternate. If any questions have come up there, just let me know. But let's start with the first one that you typed in really quickly. Right at the start, you asked, is this sound for spatial feature and object-based attention? And I imagine that you, based on the timing when you asked that, you mean whether that disappearance of attention to the left as we go into drowsiness, whether that happens for other types of things, all right?
Right.
So, Corinne?
So can you ask the question again? You're asking...
Maybe let me come to the sort of the most, in a sense, in the basic question first. From the sort of subjective phenomenological point of view, the people actually report losing the phenomenology on the left side during the drowsiness. That's sort of, really the most lingering kind of question, because I don't, if I'm not asked, I probably wouldn't say that, right? But your behavioral evidence seems to suggest that it's something like neglect. So that's a kind of conflict I've been having.
Yeah, I mean, I guess what's interesting about this is it's not that people are missing. They're failing to respond to tones on the left. They're still making a response. It's just that they're misallocating where the tones are in space. So it's kind of suggests for me that your ability to tie the features of the stimulus together is being is sort of diminishing. So the features of the stimulus, such as location, is coming away. So you can hear the tone, but you're not quite sure where it's coming from. So it's interesting that when that happens and you're faced with uncertainty, that you're more likely to respond that you believe the tone to be on the right side.
I see.
I'm wondering how you could even address the question of the subjective phenomenology of during drowsiness, because that is one of the features of drowsiness, is that you monitor yourself a lot less. I'm not even, and by asking people what their phenomenological experience is, you might be much more than you do by asking them to respond to tones, dragging them out of drowsiness and into full wakefulness again.
But we are doing some kind of an experiential sampling during the mind wandering or something like that, for example. And unless you actually ask directly what let's say spatial reference frame is like or something like that, or just ask them for draw the boundary of the visual space or something like that. I don't know how. Unless you ask it, I'm not so sure whether we can say it's difficult or not even. Have you tried asking? Probably not, right?
No, so I haven't directly asked the people what their subjective experience is in terms of where they felt the tones were coming from. Most
just
people...
visual space-wise, that did it become like this way, or just entire DS as usual experience, but as you said, things are feeling like coming from the right side. Wow. These are two,
Yeah, a lot of people often say to me, "Oh, was it meant to be that all the tones were coming from the right?" So they often say that at the end, because they felt like the tones were coming from the right. And they say that wasn't a mistake, was it? It was right that the tones were supposed to be mostly on the right. And I just don't really say anything. I said, oh, that's really interesting. That's what you experienced. So, I mean, I don't directly ask them, but what we do ask them after the study is just to sort of like draw a line on two axes of their overall subjective experience of drowsiness over time. So we do that, but certainly in terms of the spatial reference, we don't directly ask them now.
It's also, I mean, one thing about Niall's question is that people do this with their eyes closed, right?
Yeah, correct. Yeah.
Ah,
I mean, that's the whole. When you go drowsy, you're more likely to have your eyes closed anyway. So you just keep that constant across the experiment. Anyway, let's move on. Now had some other questions, but just to keep it, we'll move on to. There's a question from Ariel. Ariel, would you like me to read it out, or are you happy to ask you this stuff?
I'm happy to ask. I was just fascinated. I think it was on one of the data slides. There seemed to be a difference, unless I misunderstood the slide, in performance between the left-hand side and right-hand side, even in the awake baseline of participants. I just wondered if I'd misunderstood the slide, or if there's really a big difference even in awake people between on the left-hand side. Does that correspond to a big difference in performance between the left and the right-hand side, even in fully awake participants?
Yeah, so it does look like there's a difference here, but it's actually not a significant difference. I'm going to look at this in more depth using more powerful models, so doing like a linear mixed model or something to try and to see if that teases apart. But certainly from the original data set in 2014, there was absolutely no difference here. So these arrow bars actually overlap. So this is a different sample, and this the sample that we have are quite different in some key parameters. So that could explain why there could be a difference here. But certainly in the model that we've run and with the bond for any correction, there's no difference there in the baseline.
Right. Thanks.
No worries.
Okay, so there's a question from Angus as well. Angus, would you like to read out your own question, or should I?
Okay, I'll do it. So, I was wondering if there's something like, maybe it's related to the two models that you showed before, but like, is there something like left-right ear dominance or kind of spatial dominance, which varies, say, between people, and maybe some people, like at the group level, you see most people might make more mistakes at the left side tones, but maybe some people have some sort of dominance for the other side, and maybe they have they make more errors on the right. Do you see anything like that?
Oh yes. Hang on. So you're talking like, is this a perceptual effect? So is there do people have some kind of dominance for left-right perception? Well, I mean, I can't really speak to that. Obviously, we know that when it comes to audition, things are less crossed in the brain. But this is the individual bias scores from awake in orange and blue is drowsy. So you can see sort of for the majority of people, they show a shift from potentially maybe a little bit of a bias on the left to the right, but certainly a lot of people do start off being a little bit biased towards the right. But what's important to me is how do they move? So how do they shift from awake to drowsy? So you can see these ones are moving towards the right. But there's certainly a handful of people that go the other way. And that doesn't surprise me at all in terms of individual differences in the behaviour. But what is interesting is in a paper we published in 2015, a lot of these differences was actually related to people's handedness. And that is an important factor because the ventral attention network has been shown to be distributed differently across the brain depending on your handedness. So if you're less consistently right-handed, or if you use your left hand more for tasks, or if you are in fact left-handed, you're more likely to have your ventral attention network distributed more across both sides of the brain, or even more towards the left. And in that case, that associates with this bias. So it would be more likely that these people are less consistently right-handed. So that's one of the factors to consider as well.
Yep, thanks.
Now, are there any questions on the YouTube channel?
No, but I have several other questions actually. So linking also with next talk by Bruno, if there is a brain mechanism to this, then of course which should be, but I would expect something like this would be also found in animals. And I vaguely remember that there is some kind of inter-hemispheric competition kind of thing that has been reported in chicken and also frog and also many other animals. And if you know or if you expect, I don't know whether, Bruno, if you find any kind of, left or right bias in flies, but is there any kind of things reported in animals? And if so, then what's the sort of functional significance or meaning of this?
So as far as I'm aware, this is probably Bruno can speak to this better than I, but as far as I'm aware, there's no animal model for this interaction between alertness and spatial bias. It's not to say it isn't there. I just haven't seen anything. But I don't know, Bruno, do you have any idea?
Well, I was thinking about that while you were talking about, Jack Pettigrew's hypotheses, and I thought Stephen Miller would be pretty excited about some of this as well. And in relation, so in terms of animal models, there are a couple. I published a review with Olivia last year talking a bit about that, and the issue that was an homage to Jack Pettigrew. But I was kind of wanted to ask you also, kind of related to this, is the kind of rhythms, the shorter term rhythms that some have described that are kind of like 20 minutes long, that alternate, for example, in hemispheric switching, like also in terms of smell and things like that, not just auditory. And whether, if you look at a single subject, clearly you fall asleep, you can feel drowsy multiple times, it's not just once. Whether an individual subject is persistently, biased on one side, or whether there's any evidence of them beginning to switch to the other side, that might be some evidence of some kind of interhemispheric switching within an individual.
Yeah, that would be really interesting to look at. It's not something that we've done yet, but we could definitely do that, is to look in more depth into the individual data. And because we have the EEG there running continuously, we can use the pretrial information to obviously determine whether the person is more drowsy or more wakeful, because people cycle throughout the period. It's about 45 minutes, the experiment, and so people often get very low, but then come back up, and they might do that 6 or 7 times throughout that period. It would be really, really interesting to see how, because these networks are incredibly dynamic, and so I can imagine that as people are cycling in and out of these sort of early sleep stages, that actually we might be able to see, as you say, switching between the hemispheres. Yeah, it's a really interesting question. Obviously part of the Marsden program is to actually look on a more larger scale as to how these networks are reconfiguring with drowsiness, and to look at how the dynamics of are changing as we transition between these two states. So these are definitely questions that I'm interested in looking at. Yeah.
Also, another related question that I was asked in the chat box is that relation to local sleep. As a sort of a general kind of question, is there something known about the drowsiness and presence or absence of the slow wave that's either localized or globally observed or something like that? Because as you may have known, Thomas Andrion and Jenny Wint and I recently published a paper on mind wandering and local sleep. It may be that when you find a local sleep on the right side, then that predicts the attention shift to left, or vice versa. Like what Bruno was saying. Maybe it's kind of shifting, oscillating over the time.
Yeah, I think it's a fantastic question. For this, I'm not looking at local sleep. I'm looking at the ratio of alpha to theta frequencies across the whole brain. But yeah, I actually think it's a really good idea. I have read a lot about the local sleep and whether that might be an interesting neurocorrelate for these spatial attention biases. Yeah, it's a really good idea to have a look.
And the data would enable like a follow-up analysis to look at this kind of stuff, right?
Yeah, so we've got an incredibly rich data set because for the first time with this task, we've got individual MRIs, we've got, the EEG that we're mapping using digitization. So we have got quite a rich data set that we could go and actually ask some of these more detailed questions.
Yeah, local sleep is relatively easy to analyze as well, I
Cool.
think.
Yeah, that's a great idea.
Okay.
Are there any other questions? I don't see any other questions in the chat, but now is there anything on YouTube that you want to
No, that's fine.
Okay, and actually we're right at the half-hour mark, so it might be a good time. Thanks, Corinne, again for insight into your work.
Thank you.
Interesting discussion. And we are moving on to Bruno van Swinderen. To those of you who don't know him, I did some internet searching because I wasn't that familiar with his biography, but Bruno finished his PhD at the University of Washington in St. Louis, followed by a postdoc at the Neurosciences Institute in San Diego, where he then ran his own group for a few years before setting up his lab in 2008 at the Queensland Brain Institute. And today he will be talking to us about his work on active sleep in flies, the dawn of consciousness. So Bruno, if you'd like to share your slides with us, and feel free to take it.
Thank you, Dave. I just tried to share my screen. I tried to share my screen. I quickly noticed that that Zoom had an update that is forcing me to quit and reopen.
Ooh, okay. That usually takes about a minute. I'm sure we can find ways to occupy ourselves in the meantime.
Really annoying.
Yeah, is there any other questions maybe we can take? Or
I was wondering about your comment now about, so a lot of the discussion of whether it happens in animals or not, the discussion here focused on interhemispheric switching, but less on things like a hemispheric bias. So that's my knowledge. A lot of the literature on hemispheric biases in humans assumes that lateralization comes from accommodating functions that are not found in animals, like language, for example. So I wonder how much. I don't actually know the consensus on this right now. Whether lateralization. I know that like left and right-handedness, for example, are a lot less prominent in great apes that don't have language.
But as far as I know, when you put the animals under the sort of attentional competition kind of situation, like eating and also watching predator and so on, they start to show some kind of lateralization, even in frogs or chickens and so on.
All right.
Yeah. Anyway.
All right. So Bruno's back with us, and I see that you've successfully shared your screen. So yeah.
You can see that?
Yeah.
Okay, thank you, David. And now, I've been noticing that my video every so often cuts out. So just tell me if it also prevents me from, showing slides. Just interrupt, I guess.
Cool.
I'll just start off. I think pretty controversial subject that we hopefully generate some discussion. But here's a slide already just to kick it off with, which is a slide I used at the ASSC 18 back in the day when we organized a conference on consciousness in Brisbane, and then there's a picture of me and now at the beach in Byron Bay. And that was a panpsychism meeting that followed the consciousness conference, where the question was raised about is consciousness in a way everywhere and measurable in everything from like a chair to a human. And I think we might touch a bit upon that at the end, and maybe my talk will point a certain direction that I feel like is worth pursuing. And I'm not going to talk too much about data. I want to get rather quickly to some ideas I think are really interesting and worth discussing. But the data are largely centered on these two publications that came out recently in my lab by two postdocs, Lucy Tainton-Heap and Martina Grabowska. One of them on sleep, but also on attention, published in Current Biology, a paradoxical kind of sleep in Drosophila melanogaster. You can kind of imagine what that's about. And then the other one in PNAS, oscillations in the central brain of Drosophila are phase-locked to attended visual features. So some more evidence, stronger evidence that there's really something interesting happening in the fly brain that is akin to similar things happening in mammalian brains with regards to the importance of phase and oscillations to be able to regulate attention. I'll start first with an overview of Lucy's work, and this is how we looked at recently at sleep in the fly brain. a lot of what we had done in the past in the lab is electrophysiology and behavior, and here we really wanted to look into the fly brain, as many neurons as possible, thousands of neurons at once, to see what happens during spontaneous sleep. And that involves a fancy microscope called a 2-photon microscope that samples sections of the fly brain. Here's a fly walking on a ball. Sections of the fly brain optically to get a volume of brain space, and recording a GCamp, a calcium signal in neurons throughout a volume of about 100 by 100 microns. And we're basically looking through a window in the fly's head to the central brain. And we can look at that dynamically through time. And the fly is actually kind of sitting on an air-supported ball, as you can see here. And we're looking into the head from the top over here. And through a variety of metrics and ways of convincing ourselves, we know that the fly is falling asleep in this preparation. It doesn't fall asleep easily. It must be somehow similar to the EEG cap in somebody's lab. You're hoping somebody falls asleep, and that's the last thing they want to do in that context. It's similar to flies in this context, but we sleep deprive them basically beforehand, and then they're more likely to fall asleep under the 2-photon, and they do. And we have various metrics related to arousal thresholds that convince ourselves that they're actually asleep here. So they fall asleep in this context, and then we, at the same time, monitor their movement. And any session that's longer than 5 minutes of immobility, complete immobility, we're calling sleep, and there's a history in the flies for looking at it that way. So you can see here an example from a single fly that's been moving quite a lot in the beginning, and then had a first sleep bout after the first hour on the ball, and then another short sleep bout, and 2 other sleep bouts. So now, obviously, we're very curious to know what happens at a neuronal level in the fly brain when it's falling asleep, and how's that different from wake. And this just shows the kind of data that we get. So this is the same fly that's on the left panel, right? The same sleep bouts, except on the y-axis you have several hundred neurons. The calcium signals, each row is a different neuron. And you can see there's a lot of interesting activity and dynamics happening in the fly brain during wake. And you might already get a sense over here in the middle, like during this first sleep bout, it just looks a little bit less active, right? And then we can pick out a certain sleep bout and then look at the percent of neurons active in our group, in all the ROIs through time. And then we start to see very interesting patterns, right? That in early sleep, for the first 5 minutes, the brain is actually as active as during wakefulness for up to 5-6 minutes. And then it goes into a stage of sleep where it's mostly quiet, right? Almost very few neurons are active in the fly brain. And then it cycles. It can go back into a more active stage, and then another deep or quiet sleep stage, and then before waking up, something that looks akin to wakefulness again. And this largely looks like something that we might call sleep stages. And we're calling it active sleep, right? And not deep sleep, but quiet sleep, which might be also a better, description of what happens in other brains as well, right? So what we're calling deep sleep in the mammalian brain is a very neocortical definition of sleep that is based upon technology that we started having, namely EEG, to look at cortical activity, and an oddity of the mammalian and bird system, which is a delta slow wave sleep. And it's really many more animals that display sleep stages. It's more that the brain is quiet, and it looks like even in the smallest brain now, it's either quiet or it's active. It's not really REM. Obviously, flies don't have rapid eye movement, and it's not delta. It's active sleep or quiet sleep. And this also kind of matches earlier work that we published using electrophysiology, where we had shown a similar thing, but then just looking at local field potentials in the brain, where it was again like very quiet or more oscillatory, like something that we saw that was more in the 7 to 10 hertz range that happened during active sleep. And this also matches behavioral data where we showed using arousal thresholds that flies had periods of increased arousal or decreased arousal during sleep. So together, collectively, there's a lot of evidence now that the smallest animal brains, sleep is fairly complex. It's not as simple as just turning off. It's actually, they're cycling through different stages. So we're now really interested in understanding what the different functions are of these different sleep stages. So clearly they must be achieving something. And where it's kind of pointing to, there's 2 papers that we published recently. There's another paper in addition, a collaborative paper where we found that during deep sleep in flies or quiet sleep, it's really a time for cellular homeostasis, where there's a lot of debris clearance or metabolite clearance that happens during that stage, and that kind of matches the work that has been done by others, such as Nedergaard, showing that that slow wave sleep is associated with metabolite clearance, and it seems to be that during deep sleep something similar, or quiet sleep something similar is happening in the fly brain, where it has it goes into bouts of proboscis extension, and it's using this kind of mechanical mechanism to clear waste from its brain, and that maybe is the evolutionary antecedent of delta sleep, where a similar mechanism is happening, but there it's generated by the brain in a way as delta activity that is somehow associated with this ancient sleep function, which is to just clean the brain and repair the brain. And that's quiet sleep. And we published that with our collaborators in Science Advances, and that is matched then by active sleep, which seems to be more about a level of cognitive homeostasis. And we did some work showing that there's a connection between this active sleep stage, which we can induce optogenetically now in the fly, and I can talk a bit about that at the end, how we do that. There's a connection between that and selective attention as a way of curating selective attention. Now, sleep is also complex in other invertebrates too, right? It's not only the fly. Others have shown this now. There's more and more evidence now. For example, there was a paper in 2019 on REM sleep in cuttlefish. And there it's particularly impressive because you can actually see how their chromatophore patterns change during sleep. And it's like this visual readout of their dreams, basically. So it's really interesting, not necessarily their dreams, but what's happening during REM sleep. And they're asleep, right? They're unresponsive to the outside world, but their colors are changing phenomenally in these short spaces of time, and that clearly must be disadvantageous because there's suddenly a target that's unresponsive and suddenly very visible. So it must be achieving a very important function, such that cuttlefish have this and can make themselves so vulnerable in that way. And there was a recent paper in Octopus as well that just came out this year showing the same thing. And there you can see again the field is really leaning to calling it quiet sleep and active sleep, and there's all these different transition probabilities between them. So invertebrates sleep in stages. There was early work in bees as well, right? So already in the early 2000s, Sauer and company, Journal of Comparative Physiology, showed that bees enter sleep. In their early sleep, their antennae are rotating around, and then they go into a deeper sleep stage where they're less arousable, where their antennae are kind of pointing down, and they're basically different. So let's just remind ourselves about sleep stages in humans. We've all seen these graphs. We know what they look like. That we enter, deep sleep, slow wave sleep quickly at the beginning of the night, fast first. And then there's these 90-minute cycles that alternate with dreaming. Although it's well known now that dreaming also happens outside of REM sleep. But they've largely been categorized this way, where there's this kind of priority in a way almost for accomplishing deep sleep functions first. But then there's an equally pressing pressure to accomplish REM sleep functions that accumulate towards the end of the night. And I'd like to revisit this graph that, not people debate about this, but Hobson and Friston have proposed this many years ago as a sleep ontogeny graph in humans. And I'm not sure how many of you have seen this, but it's an interesting graph to look at. I believe the latter part of it, I experienced it myself as a slowly older, getting older human being. But and I've had kids, and I know that kids sleep a lot, right? So if after they're born, kids are having basically most of their time asleep, half of that in REM sleep. But REM sleep decreases through age, right? So as you can see, as you get older, by the time you're a teenager and an adult, you have most of your sleep is slow wave sleep compared to REM sleep, which is a minority, and then you're sleeping less and less as you get older. Basically, you need less and less sleep, and that's a very interesting, believable graph. But what Hobson and Friston propose, and I'm not really sure what their evidence for this is, but I think there is some from maybe some other mammalian models or in utero studies. But they're proposing that infants in utero, before you're even born, have mostly REM sleep, right? So, and that's like in a way the original kind of like sleep stage as a human brain is developing. And when I show this slide and use it as this discussion point for students or in talks, it's always the question that comes up is like, well, what are babies dreaming about? They're just in there, in utero, it's black, there's nothing there. And that really raises the discussion point that it's not about dreams, right? Dreams are not the interesting thing here. It's about what happens during active sleep that's interesting, and what could that possibly be. And if you think about what that could possibly be, it makes much more sense why insects would also have active sleep. And one idea here that others have proposed as well is that active sleep, REM sleep, is really for curating prediction, right? So that when a brain is growing, it has to start making models of the world. It has to start, and the first model that it has to make is about its own body, right? Where does its body begin? Where does it end? What actions were caused by itself, or by something else, some other rolling over? And to start to understand, how your actions have consequences and how to make predictions about the world and whether they get satisfied or not. And that, in a way, is the first thing a developing brain, in addition to just growing and developing and making connections with the outside world, it needs to do, is to make predictions about the world. So if this is important for a developing human infant in utero, you can see how it would also be important for any animal that is exposed to the world. They have to make predictions about their world and their own environment. And that it's not that babies or infants are dreaming. It's not that flies are dreaming. It's that they somehow are doing something during REM sleep where an epiphenomenon for humans is dreaming, but it's that other thing that's important, like that other virtual reality that's happening for all brains. So the way that I kind of see it, I think this is a good way to discuss this maybe, is that, deep sleep is really kind of like quiet sleep, and it's really a mechanism that all animals have for reducing entropy, right? Things get messy, there's too many synapses, there's garbage in the brain, that things get broken that need to be repaired. And deep sleep is an opportunity to reduce entropy or reverse the second law of thermodynamics, which is basically impossible, which is maybe one reason why we die. But you don't want to do that too much, right? The tendency, if you try to simplify and decrease the number of synapses, a la Giulio Tononi hypothesis, you might need an animal to become a habit-driven creature without any flexibility. So one hypothesis we're pursuing is that active sleep then is counterbalancing the simplifying that has happened during deep sleep to maintain a level of flexibility with the environment, to optimize your reactions to the outside world and optimize your predictions in a way. Not too predictable, not too unpredictable, just surprising enough to be adaptive in an animal's environment. And that does seem to mnemonically match really well with two books by a science fiction author that I rather like, Isaac Asimov, where one book is called The Last Question. It's a short story. And it's all about the problem of the irreversibility of the second law of thermodynamics and how that is basically something that you can't undo. And the book kind of ends in this kind of strange way that the only way that it can be undone is by God. when it says let there be light, and suddenly you can start again. Unlikely, but that's the book. And then the other one is robot dreams. How is a robot ever going to be really human without having that level of kind of flexibility or emotion in a way to be able to deal with unpredictable events, right? And that interplay between the two, I think, is really interesting. So if one looks at the evolution of sleep, I think you can kind of paint it in this light, and it becomes really interesting that deep sleep functions, or really quiet sleep functions, are the ancient ones. These are the ones that were already there, potentially in jellyfish and nematodes and simple animals that didn't have brains, where there was just some cellular processes that needed to happen that were incompatible with an animal moving around. An animal needed to be still to somehow shed its cuticle and do some developmental pathways that were just, they needed an animal to be quiet in a way to be able to accomplish those functions better. And that's completely different than active sleep functions, which may have emerged later, that really are more linked to a capacity to turn off the outside world on demand, right, very quickly. And it's kind of like what we heard about in the last talk, what Corinne was talking about, that we basically have a sleep switch, that some animals have a capacity to switch off the world quickly, right? And that is completely linked to a capacity for selective attention. That if you have a capacity to turn off the world, you also have a capacity to turn off part of the world. And that's a capacity to pay attention to some things and not to some other things. And those are fundamentally interlinked mechanisms. That attention mechanisms and the sleep switch are really part of a similar evolutionary history that co-evolved together. So this is where I kind of have a kind of a debate, not a real one, he's not with him, but with Giulio Tononi, where Giulio Tononi would propose that consciousness is a kind of a ongoing linear process, kind of dependent on phi, for example, something that you can calculate for any kind of animal, from a jellyfish to a fly to a mammal. And I would propose instead that it's really linked to this capacity to turn off the world with a circuit level mechanism that allows a brain, maybe using oscillations in phase, for example, to be able to just switch off some parts of the world and not other parts of the world. And that is linked to our entry into active sleep and our maintenance of active sleep. And that has an important curating prediction. So here's Giulio, and here's his famous quote, sleep is the price we pay for plasticity. We like using Salvador Dali. I saw Corinne use that in her talk as well. And that's a slide that would kind of illustrate the memory, the persistence of memory that happens because of the price we pay for plasticity. But I'd like to discuss here, maybe onwards, is that it is active sleep, which we now suspect is happening in any animal brain. Is active sleep the price we pay to be conscious? Right? So without active sleep, we would become habit-driven, unconscious robots, and that we have this mechanism that evolution has put in there that allows us to maintain a level of adaptive subjective awareness. And that's really what active sleep is doing in a way. And then that, of course, leads to the question about consciousness in animals, right? Are all animals at some level conscious or have a subjective experience? Something, I think, a timely subject to talk about. Now has been interested in this for a long time. That's in a way we collaborated on these kind of ideas. And I'll end instead with the other Dali picture, dream caused by the flight of a bee, or a fly, I guess. I'll stop there for discussion points, but I have other slides that talk a bit more about, how we look at things in flies and how we measure these things. And I thought it was more interesting to leave it at that point.
All right. Thank you very much, Bruno. And I found the clapping reaction icon. Yeah, that's super interesting.
So it's not sharing or
I think you can keep the sharing because you might be asked to go back to certain slides. I had a question in the chat that would require going back to one of your slides, but we won't necessarily start with me. We do have several questions that have come up, and we have about 10-15 minutes to get into them. Now actually beat me to the first question. Now, do you wanna ask your question?
I actually have a lot of questions, but let's give the chance to Daisuke.
Okay.
He hasn't.
Let's start with that.
Question.
I agree.
Yeah.
So Daisuke, do you want to ask your question, or shall I read it out?
Yeah. Thanks for the talk. It was very interesting. My question is about the calcium activity you observed, and you basically discriminate awake and sleep based on whether the fly is locomoting or not. So I was just wondering, how much of the calcium activity is actually explained by flight locomotion?
Yeah, good question. So, not much, right? I mean, so there is a correlation between locomotion and calcium activity, but the fly can be not moving for a couple of minutes, or 30 seconds, and you can see just as much calcium activity as during wakefulness, right? So it's really that the calcium activity is kind of correlated to movement, but the criterion that's been used in the field that's been a good one is that if the fly has not moved for 5 minutes, you look for anything after that is sleep. And then there's a very strong correlation, obviously, with calcium activity. It mostly goes down. But the way that we really test that their sleep is by puffing air on the fly. So we do little air puffs. And if the fly is awake, it can maybe not have moved for 3 seconds, and then you do an air puff, it'll move. But if it hasn't moved for typically 1 minute, it'll have a higher arousal threshold, and it's probably asleep.
Thank you.
Okay, I suggest we move on to Angus's question next. Angus, do you want to ask your question?
Yeah, I was wondering, because you, on one slide, you drew a link between rapid eye movement and active sleep. So I was just wondering, and you brought up the octopus and the cuttlefish, so I was wondering if, in those cases, do they have actual rapid eye movement, and if there's some sort of similar thing that you see in flies?
Yeah, so I think they have something that's more equivalent to rapid eye movement in cuttlefish, but certainly not in flies, right? There's no way that we would be able to monitor. I mean, flies don't move their eyes, right? So So what we look at instead, we have looked at some other potential criteria. We've done some micro behaviors to look at their antenna, because we saw that evidence from the bee, that the bee have different antennal movements during sleep. But there we saw no evidence of like something that we might have called rapid antennal movement. There wasn't. So that was our big hope, to see that there's some rapid antennal movement. We haven't seen any of that. So and there's other things we could look at. For example, we could look at heartbeat. So fly has about 2 hertz, 3 hertz heartbeat. We could imagine that their heartbeat might be more irregular, during active sleep, as it is in mammals. So we haven't looked at that yet, but we could look at that. But right now, it really is the correlate is really just that the brain is as active, like electrophysiologically and with calcium imaging. There is one extra signature that if you look at electrophysiology in the central brain, we do something that surprisingly looks like theta. Now, it can't be theta. It's not the same thing. There's not the same architecture to generate theta in the fly brain, but we do see a marked 7 to 10 hertz oscillation during active sleep. Now, wouldn't it be crazy if somehow an oscillation has been preserved to achieve some kind of function related to prediction, which is what theta actually is. When theta has a function in place learning, but it's probably not only place learning. It's about prediction, basically. It's about an animal moving through space or moving through time and making prediction about what happens next. Is it possible that there's something similar happening in the fly brain during active sleep that is theta-like? I mean, we were very interested in figuring that out. But those are just all electrophysiological signatures. There's very few of the physiological signatures that are often markers of REM sleep in mammals.
Great, thanks.
Okay, so moving on to a question from Aniko. Aniko, do you want to ask your question, or shall I read it out?
Yeah, no, I can. So thank you for this very interesting talk. It's a very inspiring distinction between this active and quiet sleep. And I was wondering where would you put different anesthetic agents in between active sleep and quiet sleep? So I know that there are many different substances for inducing anesthesia, but would you say that, I don't know, based on what I understand, I would think that anesthesia is more similar, anesthetized state is more similar to quiet sleep. Is that correct?
Definitely. So most of half of my lab at this point actually works on general anesthesia. That's we get a lot of our NHMRC funding from. So we do look at that, and obviously we put it in this setup, right? It's an obvious thing to look at now our calcium imaging preparation under anesthesia. And there, you're absolutely right. Anesthetics induce quiet sleep. We haven't seen anything reminiscent of active sleep. We tried ketamine and carbachol as two obvious kind of at least mammalian-centric ways of maybe inducing something that could be more akin to active sleep. Carbachol maybe, but then it's also a cholinergic, agent, right? So it could be just like messing the brain up in general and making it active, making everything active. Ketamine seems to put the fly brain into like what has been called a K-hole, just quiet. It just goes quiet. So there's many.
That's very interesting, because with humans, you would exactly, ketamine is the one where you would have some kind of subjective experiences.
Yeah, but it always really, pharmacology, you have to be careful. It's about the dosage, right? So you get very different effects at different doses. And then we have this hypothesis we're pursuing about general anesthetics that they have a presynaptic effect on snare, on presynaptic mechanisms. And I think at a slightly higher dose, that is often the one that's used for surgery, it just makes the brain uncoordinated and quiet, something that doesn't basically register as any kind of real oscillations in an EEG. And that's different than any kind of postsynaptic, receptor effects. So if you have a low, like 0.3 micromolar propofol, you induce deep sleep. You go one order of magnitude higher than that, which is often the surgical concentrations, and you get something completely different. You start flatlining.
Yeah, very interesting.
Yeah, so I think we can ask those kind of questions in the fly now about what doses of general anesthetics produce something more akin to deep sleep. Sometimes when you're under light propofol anesthesia, you actually wake up feeling refreshed. I did. But then when you go under deeper anesthesia for like, surgery, you feel miserable afterwards. And that's because it's different doses and different kinds of drugs, they use the volatiles then. So they're not the same. And certainly the concentrations have completely different effects.
Yeah, thank you so much. Yeah, I'm very much looking forward to hear more and read more about this.
No, I wanna move on to ask about a couple of the bigger ideas that you mentioned towards the end. Specifically, sorry, we have someone I think who might want to go mute because we're hearing what's going on in their office. So specifically, you talked about the relationship to predictive mechanisms, and specifically this idea that they might arise in utero. And I was wondering, within this account, where do prediction errors arise? Any clashes between reality and the internal model? How are they generated? And possibly related to this, although I'm not sure, can you envision any way, in principle, to empirically distinguish Tononi's view about the gradual nature of an increase in consciousness versus your kind of non-linearity idea?
Yes, I mean, with Tononi first, I think it kind of relates to which animals. I think if you can find out which animals have active sleep and which ones don't, that's a starting point. Because if it is a mechanism of an evolutionary mechanism that started with, for example, arthropod brains and the Cambrian explosion, like when animals first started needing to have these predictive models because they were motile, that I think if we can find, which animals have active sleep and which ones don't, and which ones just have like a deep sleep mechanism, so like quiet sleep, that might be that step function that distinguishes the beginning of consciousness or a conscious animal in a way that has subjective awareness, that makes predictions about what it's going to hit next, and other animals like C. elegans that probably don't. They're just more like a heat-seeking missile that, they don't have efference copy, that kind of thing. And then to apply Giulio Tononi's phi metrics to that division might be interesting. The prediction would be that, that the ones below that division would really be a step function in terms of complexity. Animals that don't have oscillations, animals where phase doesn't matter, right? Versus animals that generate oscillations and animals that use oscillations and phase to actually do computations rather than that have feedback networks. I think that division is really interesting. That I think will potentially put a question on this kind of continuous relationship between consciousness and that Tononi likes to talk about. I mean, at least we have a way of measuring it now, and now has applied, in his lab, ways to measure it, right? So we can do it.
About the Tononi's view, before going further, can I just make one comment? Because you guys both seem to kind of assume that Tononi's view is that consciousness is kind of linearly increasing with the amount of the phi. If you read relatively recent papers by Hon and Tononi, it's written more clearly, but it's really not like that. The so-called big phi measure that previously people thought about that it correlates with the level of consciousness. That's something that you can imagine that increases as the system grows bigger and bigger. But even that, it's really very rapidly exponentially growing as the size or complexity of the brain becomes more. But even more importantly, to explain the phenomenal consciousness, like seeing the colors, objects, and the hearing and taste and all these things, we really need to think about the structure of the integrated informations, not that one single number. That's the one that we published together, right? We are now trying to compute the structure, characterization of the structure of the connectivity or kind of causation relations, and that becomes really, really rapidly, increasing in complexity. So they did a simulation with just 7 neurons, and that gives us a relationship of 10 to the 40. It's really crazy amount of the complexity in terms of the relations, and that's the kind of qualia that we are having. So the complexity of the animals going from your nice figure if you take it as a sort of contents of consciousness or qualia, then that must be much, much sharper, like this.
Fan-shaped body, if we activate that, actually induces active sleep, right? So there's a structure in the fly brain that if you optogenetically, turn that on, the fly will go to sleep, and we can call this sleep. We've done our work. And what's interesting is that, and here you can kind of see how it's just as many neurons. It's not significantly different active as during wake. And what's interesting is that we can track every different individual neurons and relate them to baseline sleep or to active sleep neurons or visually responsive neurons. In this case, these are the purple ones,
right.
And we can know who they are and show that during active sleep, they're what were previously visually responsive neurons are not responding to the outside world anymore, right? So this is kind of Corinne's experiment, but using alternate genetic tools, where we actively turn on active sleep using light, and we can see which neurons it's blocked, And it's not that these neurons are completely blocked. They actually are just engaged in different networks. We can do that kind of graph theory analysis to see, who they're talking to now, right? So they're not responding to an outside visual stimulus anymore, but they're not off. They're still active. They're just not in correlation to that outside stimulus. And this gets really interesting then, because it allows us to investigate what is, a proxy for dreams, right? That, the function of dreams is, to reactivate maybe other networks and to enable creativity, to enable other predictive opportunities, to optimize that kind of these alternate worlds in a virtual reality that makes an animal more adapted when it wakes up. That's kind of the view. And I think we can study this without being hampered by the baggage of whether a fly is conscious or not. It's like we just study the mechanisms of what active sleep could be doing.
I think this takes us back to an interesting question that Nao put in the chat earlier, and we kind of skipped over to let new people ask questions. But Nao asked, if you do the same analysis on wakeful flies, do you get similar distinctions between quiet wake and active wake?
Oh yes, that we showed that in this paper. Actually, that was a bit of a surprise. So so we saw that, and this is kind of like your mind wandering experiments.
Yes, exactly. Flies mind wandering.
Yeah. So what we definitely saw, and this is in this paper, is that, and we haven't explored it through different kinds of wake, right? Because it gets really complicated about what is it when a fly is actually walking, when it's moving one leg, the other leg, it's a brawl. There's many different dimensions there. But we did see that in the 5 minutes prior to falling asleep, so the fly is still moving, it's still walking around. We're not calling it asleep yet. It hasn't stopped moving. But in the 5 minutes prior to the moment when we said, hey, this is the moment when the sleep started, right? The 5 minutes prior to that, for all intents and purposes, looks like deep sleep. Like quiet sleep. 5 minutes of very little brain activity, but the fly walking around, moving around. Right? So sometimes sleep looks like wake, like that's what we're calling active sleep, but sometimes wake looks like sleep. Right? It gets very confusing, and it says something about the brain of even the smallest animals, that it's not like an on-off switch, right? It's
Yeah, that's very also similar. I mean, I don't know whether it's good to take an analogy, but people are doing their tasks, all the time, and they are responding, in the paper that we published. But just before they report mind wandering, or before they report mind blanking, their response gets kind of weird, like become a bit fastened or slow or missing, but they are behaving and they look like waking, and also EEG wise it shows a local non-REM sleep like kind of signs. So yeah, it's kind of interesting. But maybe let me also ask or make a comment about the global issue of what you suggested, and also that might also touch with what Corinne also presented. The hypothesis that you made about attention, and is REM sleep or active sleep price to pay for consciousness, right? You said that. I think as you know, I tend to distinguish between consciousness and attention. And what you said exactly, and what Corinne also showed today, are completely compatible with the view that active sleep or beginning of the sleep, N1 sleep or REM sleep maybe as well. The price we pay to be attention. And the attention is, this is from this point, it's a completely kind of new kind of speculation, but maybe attention is a really weird kind of thing that you put stress on the brain because it doesn't let the brain go as naturally as possible, but you kind of shift the resource or alter the local circuits in a way that it prioritizes this or that according to the behavioral goal, right? And maybe that kind of shifting of the stress result in local fatigue of the either the source of the brain that generates this kind of shift itself or shifted and overused kind of local circuits, and that needs to be normalized in terms of maybe a neuromodulator or some kind of very rapid kind of plasticity, and that may be resulting in some kind of mind wandering or mind blanking or something like what you're saying probably. Not at the level of the synaptic morphology, but maybe hormone or maybe even the glia or neuromodulator that acts much faster level.
Yeah, I totally agree. I mean, I also like the way that Thomas Andrion, your colleague, thinks about REM sleep as super attention, in a way. Yeah, I think the kind of the cognitive homeostasis hypothesis is a good one. That without REM sleep, and without the kind of emotion that's associated with prediction errors. Like every time there's a prediction error, you have an emotional response in a way, or it's often associated with emotional responses that allows to consolidate a new memory in a way to fix the prediction error. That REM sleep curates that. That if without that, you would quickly, humans or other animals would quickly become really habit driven to the kind of things that happen in their environment, and just start to generalize everything. And what REM sleep does is just expand those options to make sure that you're maintaining a level of surprise. That surprise is a good thing. Not too much surprise. Too much surprise is autism. Or too little. Or there's this balance between schizophrenia and autism that Christone talks about, and that REM sleep keeps you in the right area. To maintain that level of surprise and prediction that is important for just adaptive behavior.
Would you speculate that this is why sleep deprivation can lead to psychotic break?
Oh yeah, or the opposite, that there's a strong connection between depression and REM sleep, right? That too much REM sleep and depressives, and then and then use sleep deprivation as a way to cure depression, or SSRIs, getting rid of REM sleep. There's all this pharmacological evidence of a connection between depression and REM, and in a way, if you think about it, depression is a sense of is a loss of control, right? So prediction is about control, that you have some expectations about the world and you're in control, and if you lose that, it's not a good thing, right? You want to get that back, and typically the kind of emotional plane that depressives have is really that they're not in control, and I think there's a connection between the functions that REM sleep is having, and maybe the fact that people who are depressed, are trying to get it back by having more REM sleep, and something's not working. And I think that all has to be unpacked, right? It's not about emotions or about depressions, anthropocentric things, right? It's about predictions, right? Things that you can study in any brain, and fulfilled or unfulfilled predictions. I think that's at least from my perspective, the more productive way of looking at it, because I can't ask a fly how they're feeling.
Okay, we have, I think, a few more minutes left because it seems like people aren't in a terrible rush to go anywhere. I suggest that maybe for the last few minutes, if anyone has any comments or questions,
or maybe can we ask also ask Corinne what you think about what I and also
Corinne. Corinne, are you still with us? Do you have any comment to make? Because that last question, I think, was addressed to you as much as to Bruno.
Yeah. If not,
Corinne has her video turned off and sound might be distracted.
And there is one question from YouTube, from Benjamin. Do you have any ideas or theories how this theory would apply to something like autism, specifically relating to the theory of mind.
Oh boy, that seems like more questions for you guys. But autism, I mean, there's, you could discuss autism. But first of all, a lot of human cognitive disorders have sleep issues, right? So it's a common observation that everywhere from autism to schizophrenia to ADHD, there's some kind of sleep comorbidity associated with it, which raises then the chicken or the egg problem of like what caused what, and it's really hard to study. But certainly, one could view autism, and Friston has talked about this, right? Autism as on the spectrum of like prediction, explanations of the brain in terms of a predictor. Too many models versus too few models of the world.
Yeah, if I remember correctly, autism is explained as a sort of relying less on the prior, so less on the expectation. So they take as it is, right?
Heightened sensitivity to to external stimuli and that kind of thing.
So is there an autism model in flies?
There are, they're not. People try to anthropomorphize them and like see if flies, display anxiety-like behaviors or asocial behaviors. I review these papers all the time. Like a new autism model for flies that's based on a gene that has been shown to be connected to autism in humans. It's always a bit of a leap, and I think it's because many things are messed up, right? Locomotion is messed up in different ways. Sleep is messed up. It's hard to make that connection. So I think we really have to go back to models of the brain. Right, and which is what I like about Carl Friston's work. It's what I like about others, like back in the day, Eugene Izhikevich. How do we think the brain works, and what does it really do? And I think predictive coding, I'm sold. I think that's a good way to think about it and a way to apply it to animal models in a constructive way.
Okay, we have a couple of questions, related questions from Marta. Marta, do you want to ask, or would you prefer me to read them out?
Yeah, I can ask. It's just I'm homeschooling, so it might be a bit disruptive. I'm just wondering, how if hallucinations and dreams are kind of two sides of the same coin, in the sense that hallucinations are sort of, dreams are sort of acceptable hallucinations when we are asleep. And then at the same time, when we are asleep, sleep deprivation can lead to hallucinations when we are awake. And so, I just wonder whether the brain must hallucinate whether asleep or awake in order to promote, plasticity, as Tony would say, or reduce complexity in our models that lead to generalizability in future tasks. Just kind of a thought. I wonder whether Bruno has any comments on that.
Yeah, I think it's a very interesting thought. I think, for me to talk about dreams is difficult, right, for flies, because, I see it kind of like, there's many things happening during active sleep or even during mind wandering, maybe, of which we just get a little string of something that we relate to, which is the dream or the hallucination. But it could be just a small shadow or a small fragment of all the other things happening. And all the other things happening, I think, is the brain kind of flexing, the possibilities that it can do, right? So to prevent it from becoming a habit-driven machine, right? And that manifests as hallucinations or as dreams, but like to prevent it from just becoming something that's so hardwired that it's always going to respond the same way to everything or overgeneralize to the outside world. And, a hallucination or a dream is kind of a representation of that in a way of of flexing that value system to make sure that it remains emotionally responsive. That's why I like these paintings in a way. Just they really convey how, especially the second one with the dream caused by the flight of a bee. It's like it really, we can't afford to become mindless robots. That would not be adaptive for a fly or for a human. And our clues for that are like the hallucinations that come out sometimes or the dreams that we remember. I really see that as a good way of thinking about the brain, and how to study it is another question. And for me, it's just I'm not going to look at tigers and pomegranates and stuff. It's going to have to be prediction errors. There's no other way. And it's not only about prediction errors, right? It's about sequences, right? oddball is one very narrow category of actually the brain does sequential things, and you have to understand that those landscape of sequences that the brain wants to do, and that they can't afford to become crystallized.
Yeah, Bruno. But I think you don't need to give up the study of the dreams in flies. One thing I'm curious is that maybe you can now that you can do this calcium imaging studies, and also you are allowing the flies to also do things by your simulator and so on. You can probably replay the experience, complex kind of sequence of the experience to them, right? And then in humans also it's the case that if you replay a simple thing many times, a simple noise many times, you don't replay. But if there is some kind of story to it, and then if you play it exactly the same way, then the brain actually replays it. And I think this study of this calcium imaging to look at the population dynamics of the bunch of the neurons to see the sequential pattern of the things, maybe a way to get to the replay first of all, and then to see whether this during the active sleep whether the replay is played like in the case of the rats or mice, Matt Wilson's study. Maybe in their case it's a replay in the non-REM sleep, but replay, hallucination, dream.
Yeah.
Maybe with your technique you can do it.
I'm a big believer of closing the loop of feedback, biofeedback being a good way to understand something, and that's one way where it could be applied. But it's going to require some machine learning methods that I'm not really good at this point. I need a good postdoc to do this to know how to gather that information of thousands of neurons at once and get something to feed back, right? And what's meaningful and what's the same and what's different. But yeah, that's definitely the way to go. I think it's and it's in the fly. It's manageable, right? It's at the end of the day, it's in the part that matters. It's like 50,000 neurons.
Can I?
Yeah.
This prompts a question that always, at some point, always occurs to me whenever I read your work and work with other people working on much simpler organisms. There is no way to answer this, but I do wonder, at a personal level, do you believe that flies are conscious in a sense that is similar to our consciousness?
Yeah, I think I do actually. I think they have a subjective awareness. So two flies looking at the same object are going to be seeing it differently, right? You can show like a competition of objects, and one fly will have one movie in its brain, so to speak, and another fly might have a completely different movie for exactly the same presentation. And that's a level of subjective awareness that I think is necessary for any motile creature to be adaptive, And now they just don't have our history, obviously. And that's where, we get what we call consciousness, is the interaction between that phenomenon, that subjective awareness, and our own history. That's where it gets interesting for us, right? But the mechanisms are there. They just have a different history, right? So I think it's not going to prevent me from doing fly research. I still grind them up by the thousands, But, I do hesitate, I have to say, if I was forced, to work on monkey work or I probably would have like a bit of a problem with that. And I wouldn't say this, too publicly. I mean, I think neuroscience must proceed in the best ways possible. Many people do very valuable monkey work, but I think you can answer a lot of interesting questions with the smallest animal brains, that are basically the same questions, So whether they're conscious, I would lean towards yes. I think every animal. I think consciousness is something that happened very early on in motile creatures that needed to predict what happened next, and they have a level of subjective awareness. It's there. They've got oscillations. They do what they need to do to be able to understand their way in the world and have an understanding, basically.
What's your view, David? Do you think that there are many facets of consciousness, like the wakefulness, for example, versus sleep? You don't believe that there is something in the flies?
Oh no, when I said I'm curious, it's because I am genuinely curious what people who do this kind of work believe. My personal belief is that there is something it's like to be a fly. I'm super liberal in that sense. I think more than even most consciousness researchers. but I'm also acutely aware that this is one of those questions that, for the foreseeable future, from a scientific point of view, will remain a matter of belief. Just because we have no objective way to calibrate our tools.
From the fly community, the view has typically been much more. It's interesting that the support of this kind of view is coming from people like you. Or now, the fly community, I have to be really careful with any of this, because they've always seen the fly as being a bag of reflexes, for lack of a better phrase. Like input-output systems without any kind of reverberation on the inside, and in a way that determines how they study the fly, right? They've got the connectome, they've got the GAL4 UAS system. They're going to try to understand it like a car. You take out the carburetor, it doesn't work. What's the minimal part required for this or for that, rather than seeing it as a whole that has to work together to produce things like oscillations and phase. So I think I'm definitely kind of an oddball in the fly community of seeing it this way, and that puts me in the dangerous position of sounding like a flake, And I always have to, when Nao and I publish together or talk together, I always have to put the reins on Nao's phrases of consciousness in the fly. But I think he's right. I think there's something there that that he's sensed early on that I think the evidence is pointing to that it's not primary conscious. It's not obviously anything remotely like a dog or a human, but there's something feels like to be a fly. Yeah.
Oh.
Yeah, so the way you asked David, before further, if you ask really, is fly experiencing something like us, then, obviously that's unlikely, because, we know that, there are many cognitive, functions that are already not there, like self-awareness, a complex working memory or thinking, many kind of different complex planning and so on. And as long as that is ruled out, it's very primitive kind of thing, more simpler thing, which we can't even imagine that. But, even that, which is sort of, proportional to the size of the number of brains and number of neurons, then still, if you can completely think about it as a pure bag of reflexes, I don't know, we need to really have a better kind of experimental evidence not to suggest that, but it's very difficult to imagine how come all these things are just a collection of extremely simple reflex.
But reflex is just a word for something we don't understand, right? So at the end of the day,
yeah, that's right. Yeah,
I think the one way to study this and what the way that we were doing, and I'm very happy to be back in the lab myself. After years of sitting behind a desk, is to do feedback from the brain, to pull out these measures that we think are attention, phase locking between endogenous 20 to 30 hertz oscillations and frequency tags. Take out these measures directly and have them determine decision making. Right? So if the fly brain can kind of go where it wants to go and learn that it can actually do it with its brain, you can actually ask some really interesting questions about not consciousness, but about decision making and about salience and about attention.
So where it comes down to a matter of belief is whether being a bag of reflexes, assuming those reflexes are complex enough, is in itself sufficient to yield or to generate the what it's like sense of things. And that to me, yes, of course, flies will have a whole bunch of cognitive mechanisms that exist in humans, but to the extent that there are processes that exist in humans and other so-called higher animals that we think are associated to consciousness, if they exist in animals like the fly as well, then it seems to me that the burden of evidence is on those who deny consciousness to the fly rather than on those who believe that it's there. If we assume, for example, that predictive processing is at the root of conscious experience in humans, and predictive processing exists in the fly, then there has to be an argument for why that same process that is at the root of consciousness in humans does not have the same influence in the fly.
About that, I disagree, but about the importance of predictive processing and consciousness. But
if you accept that, I'm not sure I accept that, but if you accept that.
Yeah. And recent survey seems to suggest that many people believe most that predictive processing is related to consciousness, right? There is some preprint going around.
Yeah, I think Ariel just put it on in the chat here. it does look very interesting.
Yeah, it's an exciting time to talk about these things, right? So the world is changing. You can be political about this if you want. Maybe we should be thinking about consciousness in every creature, right? Maybe we should be thinking about the importance of dreams. There's even sociologically, like I have a dream. These things resonate. Dreaming makes us human. Without dreams, we would become habit-driven, misogynistic, racist robots. It's just it resonates.
One could argue that you can be all those things and still be conscious, but I mean, there are many things that I think about certain figures in world politics that make me not like them very much, but don't actually make me think they're not conscious.
They're not conscious? I don't know. I'm not sure that people like Donald Trump got much sleep while they were president. Or they're probably taking a lot of sleeping pills that are just giving them deep sleep and, taking out the garbage, but not maintaining their humanity.
Yeah. Okay. Corinne, by the way, sent her apologies. She had to leave at 1:30. And I think this has been a really interesting discussion. Unless anyone has any final comments or burning questions that they want to add, I think this might be the right time to draw it to a close. So, any final words? All right. In that case, I'd like to thank our speakers again, both Corinne, who's no longer here, and Bruno, for very interesting talks and a fascinating discussion. And yeah, see everyone again next time.
Thank you very much.
Thank you.
Yeah.
Bye, everyone.